Hello, welcome back. Let's continue. So I was on my online banking and transfer like $250 or 1,500 Danish kroner, and then I buy a bigger steam engine. I buy with a bigger boiler. Half of this boiler is 250 milliliters. The other boiler is 500, is half a liter. And I have a real manometer, and I have a water drain. You can empty the boiler, and I think this wheel is a little bit bigger. The cylinder is bigger maybe, and the pistons. So I will get that in like 1 week. So, but I have just eat a little bit food. My video is not ready yet, but I don't like to wait because I like to continue. So we could read about the boiler and cylinder and all kind of stuff. I look through this, but I have some steam engine read list far down in my big file. So, but let's just try to continue. So I have to look my cell phone. I need to charge my cell phone a little bit, but we can do that later. So it's soon is 4 p.m. soon, and I did sleep after 3 p.m. a.m. night, so I'm a little bit tired today, but I got a shaving and a shower, and I got a little bit to eat now, and I think I will eat that pizza, a frozen pizza later. I have in my deep freeze. Let's continue.
Engines. A method to lessen the magnitude of energy loss to a very long cylinder was invented in 1804 by British engineer Arthur Wolff, who patented his will.
Yes, we can read for the top, of course.
High-pressure steam is admitted into the working cylinder. Much of the high-temperature steam is condensed as water droplets onto the metal surfaces, significantly reducing the steam available for expansive work. When the expanding steam reaches low pressure, especially during the exhaust stroke, the previous slide posited water droplets that had just been formed within the cylinder forward/ports now boil away, re-evaporation, and this steam does no further work in the cylinder. There are practical limits on the expansion ratio of a steam engine cylinder, as increasing cylinder surface area tends to exacerbate the cylinder condensation and re-evaporation issues. This negates the theoretical advantages associated with a high ratio of expansion in an individual cylinder. 57. Compound engines. A method to lessen the magnitude of energy loss to a very long cylinder was invented in 1804 by British engineer Arthur Wolff, who patented his Wolff high-pressure compound engine in 1805. In the compound engine, high-pressure steam from the boiler expands in a high-pressure (HP) cylinder and then enters one or more subsequent lower-pressure (LP) cylinders. The complete expansion of the steam now occurs across multiple cylinders, with the overall temperature drop within each cylinder reduced considerably. By expanding the steam in steps with smaller temperature range within each cylinder, the condensation and re-evaporation efficiency issue, described above, is reduced. This reduces the magnitude of cylinder heating and cooling, increasing the efficiency of the engine. By staging the expansion in multiple cylinders, variations of torque can be reduced. 18. To derive equal work from lower pressure cylinder requires a larger cylinder volume, as this steam occupies a greater volume. Therefore, the bore, and in rare cases the stroke, are increased in low pressure cylinders, resulting in larger cylinders. 18. Double expansion. usually known as compound, engines expanded the steam in two stages. The pairs may be duplicated, or the work of the large low-pressure cylinder can be split with one high-pressure cylinder exhausting into one or the other, giving a three-cylinder layout where cylinder and piston diameter are about the same, making the reciprocating masses easier to balance. 18. Two-cylinder compounds can be arranged as cross compounds. The cylinders are side by side. Tandem compounds. The cylinders are end to end, driving a common connecting rod. Angle compounds. The cylinders are arranged in a V, usually at a 90 degrees angle, and drive a common crank. With two-cylinder compounds used in railway work, the pistons are connected to the cranks as with a two-cylinder simple at 90 degrees out of phase with each other, quartered. When the double expansion group I duplicated, producing a four-cylinder compound, the individual pistons within the group are usually balanced at 180 degrees, the groups being set at 90 degrees to each other. In one case, the first type of Vauquelin compound, the pistons worked in the same phase driving a common crosshead and crank, again set at 90 degrees as for a two-cylinder engine. With the three-cylinder compound arrangement, the LP cranks were either set at 90 degrees with the HP one at 135 degrees to the other two, or in some cases, all three cranks were set at 120 degrees. The adoption of compounding was common for industrial units, for road engines, and almost universal for marine engines after 1880. It was not universally popular in railway locomotives, where it was often perceived as complicated. This is partly due to the harsh railway operating environment and limited space afforded by the loading gauge, particularly in Britain, where compounding was never common and not employed after 1930. However, although never in the majority, it was popular in many other countries. 58. Multiple expansion engines. An animation of a simplified triple expansion engine. High-pressure steam, red, enters from the boiler and passes through the engine, exhausting as low-pressure steam, blue, usually to a condenser. It is a logical extension of the compound engine, described above, to split the expansion into yet more stages to increase efficiency. The result is the multiple expansion engine. Such engines use either 3 or 4 expansion stages and are known as triple and quadruple expansion engines respectively. These engines use a series of cylinders of progressively increasing diameter. These cylinders are designed to divide the work into equal shares for each expansion stage. As with the double expansion engine, if space is at a premium, then 2 smaller cylinders may be used for the low-pressure stage. Multiple expansion engines typically had the cylinders arranged in line, but various other formations were used. In the late 19th century, the Yaroslik-Tweedy balancing system was used on some marine triple expansion engines. Wyast engines divided the low-pressure expansion stages between 2 cylinders, one at each end of the engine. This allowed the crankshaft to be better balanced, resulting in a smoother, faster responding engine which ran with less vibration. This made the 4-cylinder triple expansion engine popular with large passenger liners, such as the Olympic class, but this was ultimately replaced by the virtually vibration-free turbine engine. It is noted, however, that triple expansion reciprocating steam engines were used to drive the World War II Liberty ships, by far the largest number of identical ships ever built. Over 2,700 ships were built, in the United States, from a British original design. The image in this section shows an animation of a triple expansion engine. The steam travels through the engine from left to right. The valve chest for each of the cylinders is to the left of the corresponding cylinder. Land-based steam engines could exhaust their steam to atmosphere, as feed water was usually readily available. Prior to and during World War I, The expansion engine dominated marine applications, where LI vessel speed was not essential. It was, however, superseded by the British invention steam turbine. New air speed was required, for instance in warships, such as the Dreadnought battleships, and ocean liners. HMS Dreadnought of 1905 was the first major warship to replace the proven technology of the reciprocating engine with the then novel steam turbine. 59 types of motor units. Reciprocating piston. Double-acting stationary engine. This was the common mill engine of the mid-19th century. Note slide valve with concave, almost D-shaped underside. Schematic indicator diagram showing the 4 events in a double piston stroke. See, monitoring and control, above. In most reciprocating piston engines, the steam reverses its direction of flow at each stroke, counterflow, entering and exhausting from the same end of the cylinder. The complete engine cycle occupies 1 rotation of the crank and 2 piston strokes. The cycle also comprises 4 events: admission, expansion, exhaust, compression. These events are controlled by valves often working inside a steam chest adjacent to the cylinder. The valves distribute the steam by opening and closing steam pores communicating with the cylinder end, S, and are driven by valve gear, of which there are many types. The simplest valve gears give events of fixed length during the engine cycle and often make the engine rotate in only one direction. Many, however, have a reversing mechanism which additionally can provide means for saving steam as speed and momentum are gained by gradually shortening the Q-taff, or rather shortening the admission event. This in turn proportionately lengthens the expansion period. However, as one and the same valve usually controls both steam flows, a short Q-taff at admission adversely affects the exhaust and compression periods, which should ideally always be kept fairly constant, if the exhaust event is too brief. The totality of the exhaust steam cannot evacuate the cylinder, choking it and giving excessive compression, kickback. 60. In the 1840s and 1850s, there were attempts to overcome this problem by means of various patent valve gears with a separate, variable Q-taff expansion valve riding on the back of the main slide valve. The latter usually had fixed or limited Q-taff. The combined setup gave a fair approximation of the ideal events, at the expense of increased friction and wear, and the mechanism tended to be complicated. The usual compromise solution has been to provide lap by lengthening rubbing surfaces of the valve in such a way as to overlap the port on the admission side, with effect that the exhaust side remains open for a longer period after cut-off on the admission side has occurred. This expedient has since been generally considered satisfactory for most purposes and makes possible the use of the simpler Stevenson, Joy and Wolskiewicz motions. Corliss, and later, Poppet valve gears had separate admission and exhaust valves driven by trip mechanisms or cams profiled so as to give ideal events. Most of these gears never succeeded outside of the stationary marketplace due to various other issues including leakage and more delicate mechanisms. 58, 61. Compression. Before the exhaust phase is quite complete, the exhaust side of the valve closes, shutting a portion of the exhaust steam inside the cylinder. This determines the compression phase, where a cushion of steam is formed against which the piston does work whilst its velocity is rapidly decreasing. It moreover obviates the pressure and temperature shock, which would otherwise be caused by the sudden admission of the high-pressure steam at the beginning of the following cycle. Lead in the valve timing. The above effects are further enhanced by providing lead, as was later discovered with the internal combustion engine. It has been found advantageous since the late 1830s to advance the admission phase, giving the valve lead so that admission occurs a little before the end of the exhaust stroke in order to fill the clearance volume comprising the ports and the cylinder ends, not part of the piston swept volume, before steam begins to exert effort on the piston. 62. Uniflow, or Uniflow, engine. Animation of a Uniflow steam engine. The poppet valves are controlled by the rotating camshaft at the top. High-pressure steam enters, red, and exhausts yellow. Uniflow engines attempt to remedy the difficulties arising from the usual counterflow cycle where, during each stroke, the port and the cylinder walls will be cooled by the passing exhaust steam, whilst the hotter incoming admission steam will waste some of its energy in restoring the working temperature. The aim of the Uniflow is to remedy this defect and improve efficiency by providing an additional port uncovered by the piston at the end of each stroke, making the steam flow only in one direction. By this means, the simple expansion Uniflow engine gives efficiency equivalent to that of classic compound systems, with the added advantage of superior part load performance, and comparable efficiency to turbines for small engines below 1000 horsepower. However, the thermal expansion gradient Uniflow engines produce along the cylinder wall gives practical difficulties turbine engines. A rotor of a modern steam turbine used in a power plant. A steam turbine consists of one or more rotors, rotating discs, mounted on a drive shaft, alternating with a series of stators, static discs, fixed to the turbine casing. The rotors have a propeller-like arrangement of blades at the outer edge. Steam acts upon these blades, producing rotary motion. The stator consists of a similar, but fixed, series of blades that serve to redirect the steam flow onto the next rotor stage. A steam turbine often exhausts into a surface condenser that provides a vacuum. The stages of a steam turbine are typically arranged to extract the maximum potential work from a specific velocity and pressure of steam, giving rise to a series of variably sized high and low pressure stages. Turbines are only efficient if they rotate at relatively high speed, therefore they are usually connected to reduction gearing to drive lower speed applications, such as a ship's propeller. In the vast majority of large electric generating stations, turbines are directly connected to generators with no reduction gearing. Typical speeds are 3,600 revolutions per minute, RPM, in the United States with 60 Hz power, and 3,000 RPM in Europe and other countries with 50 Hz electric power systems. In nuclear power applications, the turbines typically run at half these speeds, 1800 RPM and 1500 RPM. A turbine rotor is also only capable of providing power when rotating in one direction. Therefore, a reversing stage or gearbox is usually required where power is required in the opposite direction. Steam turbines provide direct rotational force and therefore do not require a linkage mechanism to convert reciprocating to rotary motion. Thus, they produce smoother rotational forces on the output shaft. This contributes to a lower maintenance requirement and less wear on the machinery they power than a comparable reciprocating engine. Turbinia, the first steam turbine-powered ship. The main use for steam turbines is in electricity generation. In the 1990s, about 90% of the world's electric production was by use of steam turbines. 3. However, the recent widespread application of large gas turbine units and typical combined cycle power plants has resulted in reduction of this percentage to the 80% regime. For steam turbines. In electricity production, the high speed of turbine rotation matches well with the speed of modern electric generators, which are typically direct connected to their driving turbines. In marine service, pioneered on the Turbinia, steam turbines with reduction gearing, although the Turbinia has direct turbines to propellers with no reduction gearbox, dominated large ship propulsion throughout the late 20th century, being more efficient, and requiring far less maintenance, than reciprocating steam engines. In recent decades, reciprocating diesel engines, and gas turbines, have almost entirely supplanted steam propulsion for marine applications. Virtually all nuclear power plants generate electricity by heating water to provide steam that drives a turbine connected to an electrical generator. Nuclear-powered ships and submarines either use a steam turbine